So I'm going to talk about counting curves on K3 surfaces. This is a K3 surface, and I stole that from a website. You can buy that for 200 euros, I think. So I'm going to consider counting curves, algebraic curves on the K3 surface. And so if I have a non-singular projective K3 surface, it has a Picard. This is a group of line bundles, and it comes from taking the integral cohomology and intersecting with the 1, 1. And the very first question you can ask is, what is the dimension of the space of curves on a K3 surface? And there's two invariants of the curve. One is the class, and the second is the genus of the curve. And there's an expected dimension formula. This is the dimension formula in Gromov Witten theory. And it's a very simple formula. It says if you have any target, here is the K3, but if I have any target, and I look at holomorphic maps of a genus G curve to that target with some class, the answer is given by a more or less Riemann-Roch calculation. And it's here, and the answer for the K3 surface is very simple to remember. It says that actually the space of genus G curves in a K3 surface is G minus 1. That's the calculation that comes from Riemann-Roch. And the way this calculation comes, it comes from a tangent and obstruction space. And the obstruction space for the map here is this H1 of the pullback of the tangent bundle. I mean, this is, in general, maybe I should just say this, we're looking at a map from a curve. So this K3 surface. If I want to know what kind of moduli this map has, I have to look at there's the deformations of this map, and more or less in any geometry, if I have a map and I want to move it, then the deformations are H0 of the pullback of the tangent space. Right, there's a tangent bundle here, I pull it back and I take a section. And that gives me the infinitesimal deformations of such a map, because I just specified every point a tangent direction, which tells you where this map is supposed to go. So that's the deformation space, and then there's an obstruction space. The obstruction space, to understand what this means, is a much more subtle business. It has to do with deformation theory and algebraic geometry. But one imagines this moduli space, it's clear this is the deformation space, that's the obstruction space. And what happens for K3 surface is something slightly magical. It says that this obstruction space admits canonically a one-dimensional quotient. So here, there's H1, and because it's a K3 surface, the tangent bundle is isomorphic to the cotangent bundle. And the cotangent bundle, we have a map this way by the differential. Okay, so that's the magical aspect of the K3 surface. This obstruction space is very special as a one-dimensional quotient. So if I just take the regular virtual class from the moduli space of curves, it vanishes. So the Gromov Witten theory of this K3 surface is trivial, and that would be an unfortunate conclusion. And the reason it's trivial is because of this one-dimensional obstruction. But nevertheless, there are curves on K3 surfaces. So Gromov Witten theory is telling you here somehow that the Gromov Witten theory is trivial. There should be no curves on K3 surfaces. That comes from this one-dimensional quotient. But as we know, that there are curves on K3 surfaces. So here's a picture of a K3 surface. This is the simplest picture of a K3 surface in some sense. I take a K3 surface, it's fibered over P1, and it has 24 nodal rational fibers. So if you're counting genus 0 curves, you'd see there's 24 of them. So the first issue in this subject is that Gromov Witten theory says that there's no curves, but in fact, if you write down algebraic K3 surfaces, there are curves. And so how is this? These facts are put together. Here's another example. A K3 surface which is a double cover of P2 branched over a sextate has 324 bitangents. So this is a picture of it. A second family of K3 surfaces, I can have a 2-to-1 map over P2 that's branched on a sextate. That's this green curve. And if I want to count rational curves in the K3, those correspond to bitangent lines. It's a classical fact. There's 324 bitangent lines. So these are the first two numbers of actual rational curve counts on K3 surfaces. There's 24 in the previous slide, 324 here. So the reason that Gromov Witten theory says that there are no curves on a K3 surface is that Gromov Witten theory is a deformation invariant. And there are deformations of a K3 surface that actually do have no rational curves. If you take a K3 surface and I take a Kähler deformation of it, and then I can find a Kähler deformation which is not algebraic, and all the algebraic curves vanish. There's no holomorphic curves on it. And Gromov Witten theory remembers that about the K3 surface because it is a symplectic invariant. And in particular, the Kähler deformations are remembered by Gromov Witten theory, and the fact that those Kähler deformations do away with every single curve, if the answer by Gromov Witten theory is correct, the answer is 0, because I can take a completely non-algebraic K3 surface. So it is true this virtual class vanishes, and it gives, this is the first issue to overcome in studying this problem. How can I count these numbers when the answer is, the Gromov Witten theory is giving me is 0? Because 0 is not, well, it would be unfortunate to give a talk on just the number 0. And the way this is dealt with is that it has to do with this trivial quotient of the obstruction space. I had defined for you this the obstruction space as a trivial one-dimensional quotient. And it's a technical point here, but this obstruction, this trivial piece can be removed. And what you get is this reduced virtual class. And for this is a new deformation theory, which involves going by hand and removing that trivial piece. And for that, the virtual dimension increases by 1 to g, and it is non-zero. And the problem of counting curves on K3 surfaces is about this class. It's not actually the straight Gromov Witten class, it's what's called this reduced class. It has a geometric interpretation, which I tell you. But it has a nice property that, for example, genus 0 curves should move in zero-dimensional families, which is what we observed in the examples. So this is the first problem, which is you take a K3 surface, you look at genus 0 curves, those are spheres, and you pick a class, and you calculate this integral. This is a zero-dimensional class, and you just calculate the number of points in it. This is a completely well-defined mathematical object. The definition here is somewhat subtle, because this uses some, I didn't mention it here, but this uses this moduli space of stable maps, that's the compactification. And the most subtle aspect is this reduced obstruction theory. This is a rather subtle thing to justify removing this one-dimensional piece from the obstruction theory. But this is now a sensible problem. It's the beginning of a sequence of sensible problems, but it's a completely sensible problem. And the answer, in some sense, is calculate the number of genus 0 curves on a K3 surface. It's a problem that, by right, should be in the history of classical geometry. There is another way to think about this contribution. And if one knows about K3 surfaces, there's a threefold, which is called the twistor family. So this is a completely different perspective. And I gave a rather complete discussion of how to get this number from taking the obstruction theory and modifying it. But there's a more geometric approach if you're familiar with the twistor space. So and if you're not anyway, I draw a picture of the twistor space. This is the twistor space. Twistor space is a threefold. So it has 3 complex dimensions. It's fibered over P1, and the special point is the K3 surface we start with. And all these other fibers are K3 surfaces, but they're Kähler K3 surfaces. They're not holomorphic K3 surfaces. And for any genus, so what happened here? Did I go back? No. So that's the picture of the twistor space. And what you can view this number, even for positive genera, is it's the number of curves that are genus G curves that occur in this twistor family. And since the genus was the dimension is increased, then what's put here is the trim class of the Hodge bundle. So that's the definition of this count in higher genera. To say what this is in words is that if I look at this twister family, all the algebraic curves have to live in this special fiber, because all of these other K3 surfaces have no algebraic curves at all. The Kähler surfaces with no algebraic curves. And these counts are counting the number of curves in this whole twister space that live on this K3 surface. That's the geometric approach. And this is just the way to define it by the standard definition. This is the number of genus G curves on this K3 surface, and this modular space is dimension G, so we have to put some integrand, and the integrand that comes is this Hodge integrand. It's the top trim class of the Hodge bundle. It's the bundle has fiber holomorphic differentials. All right, so that's more or less the definition of the problem. By deformation invariance, this number depends only on the divisibility of M in the Picard lattice and the self-intersection. So we can write, instead of this number, that's counting genus G curves of class beta, we can have genus G, M, which is the divisibility of beta in the Picard lattice, and H, which comes from the self-intersection. So that's, in a way, one can say that this problem of counting curves on K3 surfaces, either by looking at this reduced class, or you view them in the twister family, it's a problem that has three parameters: the genus, the divisibility of the class, and the self-intersection of the class. So from this point of view, it's very simple. The problem is to calculate these numbers with G, M, and H. So G is some number that's genus, so it's 0, 1, 2, 3. M is the divisibility, so it's 1, 2, 3, and H is this the self-intersection, and that starts at 0, 1, 2, 3. So it's basically three integer parameters.
Excuse me.
Yeah.
Is it true that the betas for which this number is non-zero lie on a cone?
Yeah, that is correct.
I see.
So this is saying that. This is a reasonable point. You could say that these numbers change. If I just change beta to minus beta, then I would have the same M and H. But it's true that you only want to consider betas which are, so the way to say this is you only want to consider betas which are positive with respect to the polarization of the K3 surface. Otherwise this number would be 0. So, all right, so up to now I was just telling you the problem and that this had some technical aspects. So if you don't like those technical aspects, it's better to just say that it's better to just forget everything I said and just look at this number. We're interested in these numbers N, G beta, and this number is just a count of genus G curves in class beta on a K3. So just forget everything. I mean, I gave some rather technical discussion on this, but if you just take this N, G beta, as you have this genus G curves on a class beta, and I count them. And so the rest I talked about what the answer is and how to, and roughly speaking, how to prove them. So the first part of this is this Yau-Zaslow conjecture, and this comes from the mid-90s. And it comes from the simplest aspect of this problem. So here, I write it here so you don't forget it. We can write this N G beta, or you can write it if M is the divisibility of beta. What I mean by this is beta is an element in this Picard group of S, the group of line bundles. The Picard group of S is just a direct sum of Z's. How many depends on S, but some number. Right. So any element in a direct sum of Z's has a divisibility, which is just the biggest number M you can divide by. And this lattice has intersection form, the surface intersection form, which is in Z. And by that, it's a fact about K3 surfaces that the intersection form is even. So if I take the self-intersection, there's no square here. If I take the self-intersection, the answer is an even number. Every even number I can write in this form, and that's the h. So we index this instead by n, g, m, h. So this is some kind of way of writing it instead. And it's a fact that this number depends on beta only through m and h. That's proven by properties of the K3 lattice. So we switch back and forth in this. So this Yau-Zaslow formula is about genus 0. This 1 means it's a primitive class. The divisibility is 1. And h, we're going to consider all of them. In fact, we'll always consider all the h's in this problem. The h's come together. And the reason, we'll see in a moment. So Zaslow had some, this is actually, Zaslow and I were graduate students at the same time at Harvard. And when he was a postdoc, he started considering these curve counts on K3 surfaces. And these numbers, so here's the numbers. This is the 24 that we already saw. Those are the 24 nodal fibers. And this is the 324, which we also already saw. There's a 324 bitangents to a plane sextic. These are classical numbers in algebraic geometry. This is also a classical number, although a harder number. You can just go, you could just go look these up. But he had, what came out of this was a conjecture. This is 1995. So you take this series, actually, it's comes from the cube expansion of the discriminant. This is this modular form. And it is true that if you take this and you do the cube expansion, you get these numbers. This is a fact, it's an amazing fact that was not noticed before. So these numbers had been calculated by different techniques in the classical literature. I think that probably it was up to 5 or 6, the numbers by different techniques. But it was not noticed that the series gives you the expansion as delta, the discriminant. So So Yau and Zaslow had some kind of idea that this is, there's some motivation related to mirror symmetry that led them to this problem. And the answer then became very clear. If you look at these numbers with some idea it's related to modular forms, you immediately get this. And this is the very first connection between curve counting and K3 surfaces and modular forms. So that's the beginning, in some sense, of this subject. So here's the picture. Yau and there's Zaslow. I don't know if you've ever met Zaslow. He's an interesting character. He was, besides working on mathematics, he was a member of a champion ultimate frisbee team. The team, at the same time, more or less, the team won the world championship in Sweden that year. The name of the team is called Death or Glory. And if you look at Amazon, Zaslow, if you look at Amazon, you can find a book. I'm a co-author of this big book, with Zaslow. But if you look at his books on Amazon, he has a book on the strategy of ultimate frisbee. I think that has sold more copies than the. All right. So so what we have here is this conjecture was immediately caught the interest of lots of people because it unites these numbers in classical algebraic geometry in a kind of magical way. I should say that if you approach this subject in classical algebraic geometry, these numbers are not, strictly speaking, well defined. It requires at the beginning of this lecture, I gave you this kind of technical definition of how to define them. That is a definition. Those definitions all came after Yau and Zaslow's paper. When Zaslow was considering this, these numbers are not well defined. It was not clear how you count these things. The correct definition is rather sophisticated. But
so this conjecture came before physics.
I mean, that's not correct to say. The motivation. I mean, Zaslow was a student of Vafa, and the motivation was actually from physics. In fact, it was from homological mirror symmetry. that's one thing to say. On the other hand, it's not fair to say this conjecture was entirely from physics. If we have a discussion about, actual origin of this conjecture, what happened earlier than, not very many years earlier, a few years earlier, Lothar Goethe who was really a mathematician, completely a mathematician. He was a master's student in the Midwest, in Notre Dame. And he had, as a master's project, this problem about computing the Euler characteristics of the Hilbert schemes of points of K3 surfaces, which turned out to be a really important problem. And he solved that problem, and he found that generating series of Euler characteristics of Hilbert schemes of points of K3 surfaces is exactly this way. And Zaslow knew that. In fact, you read this Yao Zaslow paper at the beginning, that they have this kind of point of view that, in some sense, this curve counting should be related to this Euler characteristic. And just if one wants to see how that fits in this, on one hand, this curve, the Hilbert scheme of points is some kind of sheaf aspect, and the curve counting is some kind of A model aspect. And there was some view about the connection on this K3 surface via homological mirror symmetry. And in fact, the motivation there was that Kontsevich, a few years earlier, had also proposed this homological mirror symmetry. And Zaslow, and that was for Calabi-Yau threefolds, the Calabi-Yau category. Zaslow wanted to think about it in a simpler case, a K3 surface. With K3 is easier. And so this was the sequence of ideas. So I think properly said it was some mixture of math and physics. But it is the case that when this conjecture was made, these things were not well defined. Those came later. All right, so where are we? So it caught the attention of mathematicians immediately, and the solution was in 1997. That's 2 years later. There were two solutions 2 years later in this primitive class, and I don't give these solutions now. But there's very nice to talk about. So that was, but still, it's a very kind of special case. It's in the case of primitive classes. Those are classes that are indivisible. And so what happens about genus 0 for M positive? If you look at all genus 0 classes, primitives are very special classes in the lattice. And this took a long time to even say properly what it meant, and so I try to explain here. So if I take a primitive class, I want to consider maps in twice that class. So if I'm going to consider imprimitive classes, the simplest imprimitive class is one with divisibility 2. And if I take a class of divisibility 2, and I look at Riemann spheres mapping, getting onto this K3 surface in a class of divisibility 2, there are two ways that a Riemann sphere can get onto this K3 surface in an imprimitive class. One way is it can be a double cover of a primitive one. That's one way. And there's another way, is that it actually is a single cover of the class of 2. So this is what's different about the imprimitive case. In the primitive case, you can double cover a primitive one, or actually be kind of an honest class, curve class 2. So we can write this number, this count, as a contribution of these double covers and these contribution of these honest contributions. Those are curves these are actually maps that honestly have images that are in this image in primitive class. And this is a map, I put some kind of moral tint to it. Of course, from the mathematics point of view, they're equal. This is an honest class, and this is a slightly dishonest one that finds a primitive one and double covers it. So one can certainly write this contribution as the sum of these two contributions. Then you have to guess somehow how to split it. And there was an obvious guess, this Aspinwall-Morrison formula. I don't discuss now why this is the obvious guess. If you think about the twister picture and you know about Calabi-Yau threefolds, it should be relatively clear this is the obvious guess. But so then you can guess this. And this perspective motivates this following question. If I have this full count, and I know it splits up, and now this one is the dishonest contribution, and that should be somehow related to the honest count in class alpha, and then you can say, what is the relation? And as I said, there's reason to believe this 1/8 from other making this following combination, which is this full count and you take away the dishonest. So this is basically standard motivation. So then the question is, what is this? Question mark. So here really a miracle occurs, which is really in some sense the beauty of the subject, is that when I take away this, the answer that I find is it's actually the primitive contribution in the class that has number numerically class 2 alpha. So this takes some time to understand. But here we're here in genus 0 in our class, we're in a imprimitive class. And this equation says that if you want to know what this number is, you subtract out the dishonest ones, and the answer is what it would have been if that class here has somebody of the same self-intersection but was primitive. So in some sense this says that properly understood, this count n should not depend on whether it's primitive or not. And this is some kind of, from the point of view of this curve counting, really a miracle. And it leads to, so here I say it in words, once this multiple cover term is removed, this number equals the value of the primitive class with the same square. So then by reindexing, we can just get rid of all of this. So this Yau and Zaslow conjecture for the imprimitive class, and this is not really due to Yau and Zaslow. I mean, it took a while to formulate this conjecture correctly. And they really didn't play a role in that. But anyway, it's called the Yau and Zaslow conjecture for imprimitive classes. That's all of them. It says that it's the value, this number is equal to the value of the primitive class with the same square once this multiple covers are removed. So I'll write a formula for this little paragraph later. But conceptually, it's saying that there's some kind of simplicity that happens here. So the brief history is Andreas Goffman checked this for a single instance, and m equals 2. It was very hard to get access to these imprimitive classes. And Li and Jung checked the full m equals 2 in 2004. This is already quite a number of years after the original Yau-Zaslow. So a complete proof for all m was given in 2008 by Klemm, Malik, myself, and Emanuel Scheidegger was here. And the argument there was really kind of a wild argument. It was to get all of the m, and it used something called this STU model, if you're familiar with so this was used a lot in the string literature and still is. But from the mathematics point of view, it's a certain anti-canonical hypersurface, a toric fourfold, particular club Yau. And then this Gromov Witten Noether Lefschetz correspondence and Borcher's relations. And then there's some amazing modular form identities that we needed that Zagier's help improved it. So there was a proof, and sometimes if you had to say in one word, why did it take from 1995 to 2008 to prove this? Roughly speaking, the reason was that for most of that time, the methods were the methods for the problem were to consider a fixed K3 surface and try to understand its geometry. It's very hard to do that, especially in imprimitive classes. And the change in perspective that happens in this work is that we consider a full one parameter family of K3 surfaces. In some sense, we consider the entire moduli of K3 surfaces. And it's aspects of that moduli geometry, so to speak, as the K3 surface varies, which lets us get all of these m. And this proof is really, in some sense, pretty crazy proof. And it gives the, it reduces, as I said, you use these three geometries, which are really complicated. It's the entire mirror symmetry in genus 0. And the reason we can use this rigorously is because it's an toric case and it's been proven by methods that come out of Giventhal, etc. Then there's this Gromov Witten Noether Lefschetz correspondence, which is a different kind of geometry. And finally, we use Borcher's results on divisors on the moduli of K3 surfaces, which is another somehow direction. And this is part of what I got the fields model for. So it uses these three things, which are already a lot of things which are not at all in the problem. And you might wonder why it's used. And finally, this is not enough. These three transform the thing that I said was a miracle into a certain complicated modular form identity, which Zagier can prove for us. And in some sense, this gives a complete, rigorous proof of everything in this genus 0, but it doesn't fully explain it. I mean, you can do all of this, and it's true, you trap everything, but in terms of actual understanding why that specific miracle occurs, I would say it does not do that, even though it proves it. I mean, mathematics can do that sometimes. All right, but nevertheless, this is only about genus 0. So now we discuss higher genus, where really nice things happen. So in this picture here, I've discussed, in some sense, I'm giving the full historical story about what happened to genus 0. I mean, this was a more or less 14-year-old story. Then I'm going to now talk about higher genus. So that has to do with maps of higher genus curves to K3 surfaces, and this is what goes under this Katz Klemm Vafa. Yeah.
So is it true that for genus 0, for every fixed n, the generating series is theory modular?
Yes, it's modular, exactly.
Oh.
Yes. So this KKV, it comes as some kind of sums of lower ones. So maybe the best way to say it is if you were interested in imprimitive, you keep modularity, but you change the group. It's not SL2 Z modular form. It's if you change the group. That's the correct thing to say. So this KKV conjecture concerns what are called BPS counts associated with these integrals, and so this conjecture comes from not so much later than Yao-Zaslow, maybe 1999, but it had come after Gopalkumar and Vafa had written papers about how to look at counting on Calabi-Yau threefolds, and in the view of this topological string theory, the proposal there is always you should change these BPS counts. And one should also do this for K3 surfaces. And this changing of the BPS counts makes precise this kind of miracle I said happened in genus 0. And to do that, we have to think a little bit about series. So if I take this class alpha and I consider all multiples of it, so alpha is some primitive class, then I write a series, and the series has two variables, a u variable and a v variable. And the BPS counts are defined by the following crazy equation. If you've never seen it, it says that if you're interested, this equation is a change of basis. This is what this question was about. And the outcome of this BPS philosophy is you shouldn't actually compute these. You should compute these. These from big N to little r. These BPS counts, and this equation, this equation is an invertible equation. It's a triangular equation. The change from this to this is conceptually very simple. Practically, it has these signs in it. But if you've never seen this formula before, it's best to just view this as a change of basis from this problem, from these invariants to these invariants. And there's nothing to this change of basis, meaning that if you know these, you can compute those, and if you know those, you can compute these. But these are much better, these R's. There's an entire theory about why one should do this, but and these guys are defined both for primitive and divisible classes. In terms of the actual data, it's the same data, but it's much better presented. I should say that this formula, if I look at the g equals 0 term of this formula, this is a minus 2. And if I look at the initial term, sine something over that same something, this gives me a d to the minus 2 as the initial term. And if I marry that with this, that gives me a d cubed. And that's the Aspinwall-Morrison, that's the d cubed is why we had a 1 over 8 in the previous one, because that was 2 cubed. And so that's the very beginning of this, and this is the full extension. All right, so in 1999, Katz Klemm Vafa gave a prediction for what these BPS counts are, and it's a great formula. So this depends on beta only through the square. So if you remember, these n's depend on beta. The n's depend on both this m and h. But we'd already seen this miracle about this m not mattering. And this is made concrete here. If you use these r's, one of the practical improvements of this r is that only through the square. But it's not obvious, and that's conjecture 1. And then once you know that, so I said this conjecture is rather surprising because it should depend on m too. But that this BPS basis has this cunning property that takes out the m dependence. So this is already good. So if I assume the validity of this conjecture, we have this RGH, and it depends only on G and H. So that's the genus and the self-intersection. The visibility is gone, conjecturally gone. Then the question is, what is the formula? And that's the formula. This BPS counts. This is Katz Klemm Vafa conjecture, it says that if you want to know these, G, R, G, H, they're uniquely determined by the following equation. So it says that, so these are these numbers. So you take this series, this is some kind of two variant. So before, if you let y equals 1, then all of these terms drop out except the genus 0 term. And you get precisely the Yau-Zaslow formula. This is this lift of Yau-Zaslow to all positive genera. Oh, here I say, if you take out limit y equals 1, then this here is just the delta up to the q. This is just the delta. And if I let y equals 1 here, well, the square root of 1 minus the square root of 1 is 0. So that all these terms drop out, except of course you take 0 to the 1, 0 to the 0, which is 1. So only the genus 0 term here, and you get exactly the Yau-Zaslow formula. So this Katz Klemm Vafa formula has these two parts, conjectures 1 and 2. Conjecture 1 captures the fact that there's no dependence on divisibility. Conjecture 2 tells you the answer. Okay, so the right side of conjecture 2 is related to the generating series of Hodge numbers of the Hilbert schemes. In the Yau-Zaslow formula, as I said, that was related to the Euler characteristics of the Hilbert schemes. And now we have the Hodge numbers. All right, so as a consequence, this BPS state count is an integer, and it's 0 if the genus is greater than h, and it has this property here. So here are these numbers. You can just, given that formula, you can just calculate them. And these are the numbers we saw before. This 124, 324. These are the very classical numbers that appear in the algebraic geometry literature. And these are all somehow new. Okay, so then the question is how, so here's Sheldon Katz, Albrecht Klemm, and Gromov Witten. All right, so I wanted to explain here to some extent this theorem. So in 2014, which is this year, we proved this full Katz Klemm Vafa conjecture, which sets, actually this theorem completes this line that started in Eric Zeslow's work. 1995, so it took almost 20 years to sort this out, but we proved that it depends only on beta through this square, so that's the first, the thing I said, the first miracle, and the second is that this actualizes the valuation holds. So I want to say a few words about how that goes. In particular, this gives a second proof of this Yau-Zaslow formula in genus 0. I mean, our proof this year does not specialize to the proof we found with the manual. It's a different proof. It is not an easier proof. I think it's, in some sense, I said this argument in our old paper was a wild argument. It's a little bit crazy. This argument has a not less amount of developed mathematics, but I think it's slightly more conceptual. For example, it does not depend on modular form identities by Donaldson Thomas. Nothing wrong with those. So now I explain the strategy of the proofs. This is the strategy of the proof from this paper in 2014 with Richard Thomas. So the first part is what's called this Gromov Witten Noether Lefschetz correspondence. This also plays a role in the earlier proof. So this is a kind of large subject. So again, we're going to move the K3 surface. We don't have a fixed K3 surface. I said this is somehow the point of the Gromov Witten Noether Lefschetz correspondence, and it's why I think that it's why there was no progress on these counts for about 10 years, because people were always considering a fixed K3 surface. But we know now we have to move the K3 surface, so when we move the K3 surface, you get a threefold. And the question is which threefold? In the previous work, we used the STU model, which is a very interesting thing. But we don't use it now. We use a much simpler thing. We look at P2 cross P1, and we blow up that as a point. That's a threefold. And this has Picard group of rank 3, because P2 cross P1 has Picard group of rank 2. We blow up the Picard group of rank 3, and here they are. And I look at an anti-canonical K3 hypersurface there. This is a nice Fano threefold P2 cross P1 blown up at a point. and I can take an anti-canonical K3, and it has a lattice 3, and that's the Picard lattice of the K3 surface. It's a nice thing. So to get a one-parameter family, I take a anti-canonical hypersurface in P2 cross P1 blown up cross P1. So the specific geometry is not so important here. I mean, of course, it is important in the proof. It's a very specific choice, but it's a one-parameter family of K3 surfaces, and they have lattice 3. So we express the Gromov Witten invariance of the threefold X. And this is the crucial point in this correspondence, is that we have a threefold. This is a Calabi-Yau threefold. It's fibers of K3 surfaces. And we express the Gromov Witten invariance of X in terms of what are called the Noether Lefschetz numbers of pi, and these things we're trying to solve for. And that's this Gromov Witten Noether Lefschetz correspondence. So a fiber class has these 3 degrees because there's the 3 polarizations. So here I write. So this is the main tool that allows, this is the starting point of the new approach to this problem in 2007 with my then student Devesh Malik. We wrote this correspondence, and it says that if you want to know these BPS states for the Calabi-Yau threefold, you can calculate them in terms of these things we're trying to solve for, the BPS states for the K3 surface, and what are called these Noether Lefschetz numbers. And what are those Noether Lefschetz numbers? So this is the Gromov Witten invariance of the Calabi-Yau threefold in these 3 degrees, and these are the Noether Lefschetz numbers. I have a picture for that in a moment. The Noether Lefschetz numbers counts the number of K3 fibers of S which carry a class beta, but square this, so divisibility m, that square, and these degrees. So here's the picture of it. This is the main thing to look at. If I take this family of K3 surfaces, that's X, it has a generic lattice. That's the lattice I gave, the rank 3 lattice. But sometimes it jumps to rank 4. When it jumps to rank 4, it means that there's a special class that suddenly appears in the fiber. And that these are the numerics of that class. And this number tells me how many times the lattice jumps. So this is really a basic algebraic geometry thing about this. If you have a K3 surface that has a lattice, if you move the K3 surface in a one-dimensional family, that lattice can jump. And in fact, it will jump. How it jumps, well, I tell you what, tells you what kind of new lattice you have. But the main thing here is how many times it jumps. And that's this Noether Lefschetz number. And that's governed by this Borchard's work. So this equation is a great equation for this problem because it intertwines 3 different pieces of geometry. This is what we're trying to solve for. That's curves on the K3 surface. This is curves on the Calabi-Yau threefold. And these are the Noether Lefschetz numbers. And this equation is a rich enough equation that for the most part, you have to pick your family correctly. That's why previously we picked the STU model, and now we pick this family. This equation intertwines the fate of these 3 actors. And roughly speaking, if you know any 2 of them, you can determine the 3rd one by this. And one of them this is this Noether Lefschetz numbers. These are modular forms that are determined by Borchard's. So this says that if you know this fellow, you can determine that, or if you know these, you can determine that. And this is used both ways. So how did the proof earlier with Albrecht, Emanuel, and Devesh, the old proof in genus 0 was a situation where we knew these by Borchard's. This is a genus 0. And we knew this by mirror symmetry, so then we could determine those. Because that was genus 0. Now, we're in higher genus, and mirror symmetry is not good enough for us in higher genus. In genus 0, not only do we need to know this, but we need to have exact formulas. And not just in principal formula, we need closed modular form formulas. And we're not smart enough at this moment to have to do this in genus G, that proof. Although afterwards we'll be able to prove those formulas, but there's a certain order of events that you want to prove. So in higher genus, we don't know this. We know this still. So the problem which stalled us for many years is we have this equation, and there's 3 unknowns, and we only know one of them. It's always sad when you have an equation with 3 unknowns, and you only know one of them. Okay, so then the progress that comes is now a completely different subject occurs, which is the stable pairs. This is what gives us the handle on this. So it's kind of late in the lecture, so everything I've been talking about is a modular space of maps. Gromov Witten theory. This is a model. We're going to switch now to a moduli space of sheaves problem. This is a problem that in some sense is related. There's a general view that if you're doing the string theory that's maps of curves, you can trade that for doing gauge theory on the target. And a precise version of this problem was, a precise version of this correspondence was proposed, well, first with Molik, Nikita Nekrasov, and Andrei Klenkov. We proposed that 10 years ago, but the one that's useful here was another one proposed myself and Richard Thomas, and it's called stable pairs, and it's a specific sheaf theoretic problem, so it's described here. I think that maybe we don't have to worry about the specific details of it. But everything is parallel to Gromov Witten theory. It's a modular space of sheaves on the threefold and has an Euler characteristic in a class. The modular problem is different. And what's crucial is that, so Richard and I proved that for this sheaf, and not during Gromov Witten theory, during this sheaf theory, you get the same correspondence. These tildes mean we take the BPS invariance in the sheaf theory, but we get the same correspondence. It's just the same as before. Before we had we had the correspondence in Gromov Witten theory. Now we have the same correspondence in the sheaf theory. Okay, so what's good about this? So we have this. So previously we had this equation here. That's the Gromov Witten equation, and then we have this identical equation on the sheaf side. So what's good about this is that with my student Pixton some years ago, we've proven that for Gromov Witten theory and stable pairs theory, these counts are equal. This is an instance of this idea of doing integration over the moduli space of maps, which is kind of a topological string theory, and this is integration over sheaves on the target, which is kind of a gauge theory. We proved they're equal. This is really kind of a long. This is really a long work in that. So that's why I said this proof is not easier than the previous one. But now, if you see what happens, there's something very nice happens. So if we go back in these correspondences, so this is the Gromov Witten correspondence. So there's the N, R, and NL. And here's the stable pairs correspondence. But we know this N is the same as the old N now. So this is a way of playing with the equation. So we know that this N is the same as the Gromov Witten N. These Noether Lefschetz numbers are the same. So we use these correspondences now to prove that the BPS states for Gromov Witten are the same as the BPS states for the stable pairs. So that's the use of this correspondence. So this correspondence allows us to change this whole problem to stable pair geometry. So all we have to do now is study this problem, and it turns out this is much easier. I mean, this good. The step of getting away from integration over the maps to actual gauge theory is much easier. That's a general philosophy. These problems, if you have a problem of curves, of kind of holomorphic maps of curves, if you can trade that for some problem of sheaves, usually it's a good trade because the geometry of a sheaf is a much more linear geometry than the geometry of a map, which is some kind of nonlinear geometry. So there's many steps here, too many to summarize. But the main thing is we can transform this problem to one about S cross C, which is the simplest Calabi-Yau. And there we can use localization with respect to the C star. You can't do this stuff effectively for curves, but for sheaves you can. And the crucial observation is that something very nice happens with the fixed points. That what's called this clean stack. And if you look at S cross P1 in the multiple covers, only these ones that stack cleanly, not like this, contribute. You can just show some vanishing. And the outcome of this is that we can just explicitly verify this multiple cover structure that is proposed by Katz Klemm Vafa. So that gives the proof. I mean, the main idea in this proof eventually is you transform everything to the sheaf problem. The sheaf problem has some subtleties, but it's much easier to handle. So that reduces it to m equals 1 case, which was proven before. So this calculations of Kawai and Yoshioka play a role. So that's that's somehow what happened in this new approach. Is it's the use of this Gromov Witten and stable pairs of Noether Lefschetz correspondence, transform everything to sheaf problems, and then use older methods. So I wanted to give one example for quartic surfaces, just to show what it is. If I look at this family of quartic surfaces, it's the simplest type of Claviers. And to show what this Noether Lefschetz, so those are explicit modular forms. I wanted to show this explicit shape of these Noether Lefschetz. Yeah, so there, that's a great thing. This is a modular form of weight 21 halves and level 8. It is this, and this is telling you with the solution for the Borchardt side, Noether Lefschetz numbers. It's this particular crazy modular form, and it was first found, so we can expand it. There it is. And this was first appeared in calculations of Klemm, Kreutzer, Zrich, and Scheidegger in 2004. We'd proven that this actually is what comes from the Noether Lefschetz theory, from the Borchardt's theory. So what happens is that this gives a complete calculation for these numbers for the Clavier threefold. So these are all calculated now, and this is comes from this Borchardt's modular form. But this is the kind of stuff that's hiding behind this proof, that in this Borchardt's form, everything's explicit, but sometimes very complicated. So one has to find a way always to deal with it without actually expanding it. Okay. That's it.
Are there any questions?
You can ask me.
Not? Let's thank the speaker again.